So hi everyone. So today I'm going to explain about design of reinforced concrete beams, and this is under chapter 4, which is the RC beam design for rectangular beams. So my name is Dr. Goh Wan Inn. Okay, so let's go to the introduction first. So the purpose of this chapter is to compile the design principles that have been previously discussed in order to form a complete design procedures of reinforced concrete beams. Okay, so what you have learned from the chapter 1, 2, 3 is all combined, and then we are going to complete design procedures of reinforced concrete beams. So basically, beam is the structural elements which subjected to transverse load in the form of bending moments, shear force, and torsions. So therefore, the beam is designed to resist all that particular factors. So beam is also designed to fulfill the serviceability requirements in order to produce an adequate and safe design. So it must be safe to use. So design principles of beam involve the design of main, which is a longitudinal and secondary reinforcement, shear links for the verticals, and checking the deflections and cracking. So let's see what is the components inside a beam. So you can see that this is the main reinforcement. Okay, at the bottom is the tensile, the AS, and this is the AS prime, which is the compression. For the top, this is a main reinforcement compression AS prime, and this is the main reinforcement tensile for the AS. And this is the concrete, okay, the overall concrete, and the shearing. Okay, so this is a shearing, and the nominal concrete covers, the concrete covers. So the design procedures. So what you have to do, you can including these 11 steps. So from the chapters before, you already learned how to determine the design life S1 to axis, okay, and then determine the beam size. Here all the standard has listed, so you can refer to the Euro code, okay, so you can get it, okay. Determine the beam size, the B time hash, and then determine the design actions on beam, which is a GK and QK. Assess durability and characteristic strength, and then determine nominal cover, calculate moments and shear force, which is the SFD and BMD, and design the flexural reinforcements in the previous section for this chapter 4, which is the AS and AS prime. And then for these following chapters, following sections, you are going to learn about design of shear reinforcement, design checking deflections, okay, and then checking of crackings, and then detailings. So the size of beam, from structural point of view, the sections of beam size is often detected by deflections control criteria. So the deflection is quite a very important criteria in design of beam. So the beam must be avoided for the deflections, okay. Okay, span to overall depth L over H ratio is 13 to 18, are generally thought to be economical in the case of simply supported and continuous beam. So we take the middle, normally we will take about 15, okay. So also how to get this also is already teach before in the preliminary beam size analysis. So the recommended ratios of width to overall depth in rectangular sections, beam section is 0.3 to 0.6, which is the B over H ratio. And beside that, the beam size also controlled by an architecture detailing and fire resistant requirement. So the beam size also we need to based on the what proposed in the architecture drawings. We cannot run away too fast, so it will affect the external appearance, and also the fire resistance, like 30 minutes, 60 minutes, and so on. We need to determine the B minimum based on the EC2 give the recommendations. Okay, so the minimum B min is based on the fire resistance from the table 5.5 and table 5.6. Okay, so this is the table 5.5 for simply supported beam. Okay, so we can check the B mins here based on the fire resistance 30 minutes, 60 minutes, 90 minutes, and so on. Okay, so for the continuous beam, this is the B min for also the standard fire resistance according to the R60, R30, R60, R90, and so on. So you can check the B mins here. So So let's go to design of fracture. So the design procedure for rectangular bin. So this is for the rectangular bin, everyone. So for French bin is similar, but the equation is different. So first we need to calculate the K. So the value of K is equal to MED over FCK BD. So also after that we need to calculate the K balance. So K balance is equal to this formula. So when the moment rate distribution is 0, okay, the theta, the sigma is equal to K balance, which is equal to 0.167. So after you get K and K balance, so you will compare K and K balance. So if the K is lesser than K balance, means the compression reinforcement is no need. So what is, you still remember the the compression reinforcement? So at the bottom is the tension reinforcement and the top is the compression reinforcement. So this is the S prime, this is the AS for the reinforcement. So when K is less than K balance, so we do not need the compression reinforcement. So after that we can calculate the lever arm Z, which is equal to using these equations, and we can calculate the AS by using this equation. Okay, so what if the K is greater than K balance? Which means we need the compression reinforcement, so we need the AS prime. Okay, so the lever arm is using these equations and the X is equal to these equations. So we need to check by using the D prime over X. Okay, so if it's lesser than 0.38, then we have to use this equation. So what if it's greater than 0.38? So we need to use these equations. Okay, so AS is equal to K balance FCK BD power of 2 over 0.87 FYKZ plus AS prime FSC over 0.87 FYK. Okay, so this I will show you the example of calculations in another videos. Okay, so don't worry. So now we go through all the equations for the item first. Okay, so now we go to the design of shear. So easy to introduce the strut inclination methods for shear capacity checks. So in this method, the shear is resisted by concrete strut acting in compressions and shear reinforcement acting in tensions. Okay, so specified in clause 6.2.1, 6.2, 6.3, 6.3 in the bracket 3 and this, you all can go through the Eurocode and reach it. So when the bending moment is in greatest condition, so cracks are caused by bending stress in the tension zone. So you can see this is all the cracks line caused by the bending moment. Okay, you can see that this is the example photo where the cracks line happen at here. Okay, so the design procedure. So first we will get the design shear force and then determine the concrete strut capacity for cot theta 1 and cot theta 2.5. Okay, so VRD max is these equations, okay, in the clause 6.2.3. So if the VED is greater than VRD, cot theta equal to 1, where theta is 45 degree, so we need to redesign the sections. If the VED is lesser than VRD, maximum cot theta 2.5, so you use cot theta 2.5 and calculate the shear reinforcement as follows. We use this equation. So all this I will show you in the examples later on. Okay, so if VRD maximum cot theta 2.5 is less than VED, but then VED is less than VRD maximum at cot theta 1, so theta is equal to this formula and we calculate the the shear reinforcement by using this equation where the maximum spacing is less than 0.75 D. Okay, and then calculate the minimum length using these equations and calculate the additional longitudinal tension force caused by the shears and the additional tension reinforcement by using this equation. Okay, so let's go to the deflections. So the deflection is very important components also. So the excessive deflection lead to sagging of floor, crushing of partitions, buckling of glass enclosure, ill lifting doors, windows, poor drainage, misalignment of machinery, and excessive vibrations. So for control of deflections, two alternative methods are described in clause 7.4. So first is the limiting span or to depth ratios, and another one is calculation of actual deflections. So you can check the clause 7.4.2 and 7.4.3 for the further information. So deflections limits the final deflections of a beam, slab, cantilever subjected to quasi-permanent load, which is to not exceed than span over 250. So for the deflection which take place after the applications of finishes or fixing of partitions should not exceed span over 52. Okay, so the deflections, the basic span effective dead ratio to control deflections to a maximum span over 250 are given as this. So when the rho is lesser than rho O or the rho is greater than rho O, you need to use these two equations separately. You need to compare. So first you need to get this PO, which is the reference of reinforcement ratio, okay, by using these equations, and rho is the required tension force by using these equations. You compare these two values to decide which is the equation you need to use. And after that, this is the basic ratio of span effective depth for reinforced concrete member without the axial compression. So this is a table 7.4n. So you can get the value of K based on the ratios. Okay, so deflections. So the basic ratios are modified in particular cases as follows. Okay, so for French axiom, French beam, you know that French beam is the French axiom, the French beam, where the ratio of the French width to the web ratio is 3, the value should be multiplied by 0.8. So for beam and slab or other than flat slab with span exceeds 7 meter, the support partition reliable to be damaged by excessive deflections, the value should be multiplied by 7 over the span. So when more tension reinforcement is provided, the SS provided is then the required. Okay, multiply the value of AS pro over AS required, but should not be greater than 1.5. Therefore, the allowable L over D will become these equations. Okay. So the procedure of deflections check. So to control the deflections to a maximum of span over 250, you have to calculate PO, P, and the rho O, rho, and then the rho prime. Determine the value of K and calculate the L over D value by using this, either this or this equation according to the condition this or condition this. Okay, so calculation of modified factor, the MS span and the MF area. So let's go to look at the cracking. So cracks are induced in reinforced concrete elements such as a result of, for the first, A, fractural tension, a tensile stress due to bending under applied load, diagonal tension stress due to the shear under the applied load, volume changes due to shrinkage, creeps, thermal and chemical effects, splitting along the reinforcement due to bonds and anchor failure. The primary objective of crack control is limit to the width of individual cracks, and this is required not only for aesthetic reasons, but more importantly is for durability and particularly for corrosions protects of reinforcement. Okay, so for crack controls, two alternative methods are described by Cloud 7.3, which is the first, the control cracking without the direct calculations, and number 2 is calculations of crack width. So control of cracking without direct calculation. So for reinforced slab in buildings subjected to bending without significant axial tensions, the specific measures to control cracking are not necessary where the overall depth is not exceed 200. Okay, so principal reinforcement, the X max is less than 0.3 as is less than 3 H or 400 mm, which is the smallest, and secondary reinforcement is need to be less than 3.5 H or less than 450, which are the smallest. And if the H is greater than 200, okay, if the H is greater than 200, then the cracking is restricted by the bar diameter or spacing. Okay, so the minimum reinforced area is according to this cloud, and maximum bar diameter is according to 7.2 and the tables. Maximum bar spacing is accordingly to the table 7.3 and. So limiting cracking crack width is in the absence of specific requirements, example like the water tightness. Okay, the crack width may be limited to 0.3 mm in all exposure classes under the quasi-permanent combination of loads. So in the absence of requirements of appearance, this limit may be relaxed to 0.4 mm for exposure class X0 to CX1. Okay, so for the cracking, the steel stress should be calculated based on the crack sections under the relevant combination sections. It can be calculated using the following equations. So conservative as sigma equal to 1 for non-redistribution moments. So you're using these AS equations. Okay, or either using this. So GK and QK are characteristic of permanent and variable actions respectively, and FYK is the characteristic strength of steel. Okay. So the maximum bar diameter of crack control is according to 7.2 N. Okay, when the steel stress is this value, so what is the maximum bar size? Okay, the WK equal to 0.3 mm, so we can check this. Okay, so preferable for single layer of reinforcement with adequate clear distance spacing as provided must be greater than the D bar or either D aggregate plus 5 mm, or which is the 20 mm. Okay, so for the maximum bar spacing for crack control, so this is the shear stress, and the maximum bar according to WK 0.3 mm, so this is the maximum bar spacing size. So preferable for multi-layer of reinforcement as long as attain the maximum diameter, the X provided must be lesser than the X maximum. So the X provided must be lesser than the value that including in here. Okay, so procedure for cracking checks. Okay, so first we start with the crack control for beam design can be directly referred to the clause 7.3. So for a convenience, crack control without the direct calculation is preferable in 7.3.3, table 7.2n and table 7.3n. So the procedure is the first, okay, calculate the steel stress for limiting crack width WK is equal to 0.3 mm. Okay, so we calculate the Fs is either using that two listed equations. So here listed one is Fs equal to using this equation from 7.2n, and then we calculate the maximum bar size or spacing from the table 7.3n, and then we get the adequate crack control, controls, which is the D bar provided must be lesser than the D bar, the diameter bar maximum. Okay, then finish, and then the area of reinforcement, the minimum area of reinforcement for beam is also specified in clause 9.2.1 as AS minimum is equal to this equation where it must be greater than 0.0013 BTD. Okay, and then the maximum area of reinforcement for both compression and tension is specified in clause 9.2.1 where the AX maximum is equal to 0.04 AC or either 0.04 B hash. Okay, so after we calculate all of that and we determine all the dimensions, so we will proceed with the detailing of reinforcement. So the minimum distance between the bar is to permit the concrete flow around the reinforcement. Okay, so the bars cannot be too congested, or else the concrete cannot flow when in pouring into the formwork. Okay, during the constructions, and to ensure that the concrete can be compacted satisfactory for the development of adequate bond. So the clear distance between the bars should not be less than the maximum of the bar size. Okay, and then the maximum of aggregate size plus 5 mm. Let's say your aggregate is 15 mm, so it must be at least 20 mm. Okay, as specified in the clause 8.2. So other aspects related to the detailing reinforcement that need serious attention are determined and coverage of reinforcement, led in the reinforcement. So you can get it in the clause 8.4 and 8.7 for the information. So detailing of reinforcement. So detailing of reinforcement in the terms of curtailments, anchorage and lap must be provided to satisfy the requirements. So we need to check the curtailment, check the anchorage, and check the laps based on all these three clauses. Okay, so this is the anchorage of bar. Okay, so you can see this is the anchorage of the bar. Okay, and then the laps for bars and also the anchorage for link. Okay, so this is the detailing of reinforcement. We proceed with the simple rules for anchorage of bottom reinforcement at the end of the support. Okay, so we put the simply directed simply support at the indirect and then simply support the direct. Okay, so AS bottom steel reinforcement at support is greater than 0.25 AS provided in the span, and LBD is required from the line of contact of the support. So this is the equation. You can take the conservative value of the alpha is equal to 1, or alpha 2 is equal to this equation. Okay, so simply rules for the curtailments of bars. Okay, so this is the formula how you do the curtains. Okay, so you can see the curtains how you can do. Okay, 0.0.8 L here for the simply supported, and this is the continuous beam. So all these values are provided, or all these formulas are provided.